Swayam Prabha. Digital India. Educated India.
Welcome back everyone, and in this module let us start our discussion of 1D rectilinear motion on a wedge or an inclined plane, right? So on a wedge we have the following. We have a wedge which is making an angle alpha with the ground, right? And we have a particle, we have this, which is this is going to slide along the surface of the wedge, and now we have to write down the force balance of the system. So let me say that the frame, so first we have to fix the frame. So the frame is such that the x direction or the I hat direction is along the motion of the particle, and of course the z direction is perpendicular to this motion, so this is my k hat direction. So the particle is experiencing a weight which is minus mg, but this minus mg is not acting in any of these directions I and k. So we have to resolve this weight along the direction I and k, right? So similarly we see that if the particle suppose also experiences friction, so the friction is a type of resistance, and this is going to act along a direction which is opposite to the motion of the particle, right? And we see then that the particle is moving normal, the normal to the surface of the particle, we will have the so called normal reaction forces, right? And then let me call this particular direction where we have the weight as my k vertical, right? So we see that the particle is, of course, due to weight, it is going to move along the I hat direction, and I resolve my k vertical along the I and the j direction. This is going to be minus sine alpha I plus cos alpha k, right? Notice that so if this is alpha, so this is my 90 minus alpha, and then I have to resolve, so I have to resolve this motion along this direction and along this direction, right, with this as angle as 90 minus alpha. So that is what the two directions are. Okay, so now I am ready to write my equation of motion. So m times, so the second law says that m times dv dt. So now the velocity, so what is the direction of the velocity? V times I hat, it is moving along I hat, right? So this is, so now the readers can quickly see the advantage of using this coordinate, because now the velocity has only one component, that is along I hat, right? Otherwise we will have two components that we have to resolve. And then the net forces acting on the particle is n times k, which is along the positive direction, and then minus f times I, and then minus mg times kv. Kv is minus sine alpha I plus cos alpha k. Okay, so now we are ready to resolve the equation of motion. So this is a vector force balance, and now we can write down the components to see that, well, there are only two components. We see that along the I direction, we have m dv dt is mg sine alpha minus f. So mg sine alpha, this is the I component and this is the I component. And then we have n times k is equal to mg cos alpha, right? So there is no acceleration along the k direction. So the net, we see that the net force balance along the k hat direction leads to the balance that the reaction forces are mg cos alpha. Now, suppose further if we assume that the friction force is 0 and we try to solve this equation, we immediately see that the equation of motion reduces to this is equal to g sine alpha. So that is our Newton's second law for this motion along an inclined plane. Now suppose this alpha, this plane becomes a vertical plane. That is, so for the special case, I think, well, for the special case, we see that alpha is 90 degrees, right? So we see that if alpha is 90 degrees, we see that the equation of motion is dv dt is equal to g, right? And we find that the body is falling, it is going to perform the same projectile motion, that is the wedge, the impact of wedge is not there, and of course the reaction forces for alpha equal to 90, the reaction forces will come out to be 0, which means that the special case of a vertical wedge will have no impact and the motion can be primarily be that of a projectile motion falling uniformly under the action of gravity. Okay, so that is as far as we can discuss in terms for the wedge equation. So let us now look at one more interesting example, that is of a pulley mass system, right? So let me just introduce a pulley system, a pulley mass system. So what we have is, let us look at, so the problem is, so what is a pulley? So suppose a pulley is typically a circular disc which is being tied with two masses on both the ends with some string, right? The string is a light and inextensible string. So what do we mean by light? There is no mass, so we don't count the mass of the string, and also inextensible means that there is no elasticity in the string, so it cannot stretch, right? So we are going to look at problems involving elasticity a little bit later, but for the time being there is no elasticity, so there is no elastic energy stored in the string. So now we have a pulley mass system and we want to understand the motion of this system, right? So these are the basic assumptions in terms of the string in the pulley mass system. Okay, so let us look at some examples of the motion of these pulley mass systems. So we have the Atwood's, so-called Atwood's machine. The Atwood's machine. So what does it say? So we have two bodies with masses, small m and capital M, where small m is less than capital M, and are connected. They are connected by light inextensible string. They are connected by light inextensible string, and the pulley system moves up. So let me just talk about this pulley system. So this is the diagram already that I have drawn here, and we want to find the upward acceleration of mass small m and the tension in the string. Okay, so we want to find with what acceleration this small mass moves, and we also want to find the tension in the string. So let me draw the force diagram here. So we have a pulley which is small m with a capital M, and now we have the system which is moving upward, right? So let me call this system is moving upward with velocity, some velocity v, which possibly is an unknown of the system, and now this small mass, since small mass is smaller than the small m is smaller than capital M, this is going to move up, right? And of course this capital M is going to move down, and we expect that if we want to write the force balance, we will see from Newton's law that m times dv dt is equal to the only forces acting on these objects are its weight and the tension T of the string. So we have that m dv dt is, this is moving up, so we have T minus mg, and on the other mass we have capital M dv dt is mg minus T. Why the change in sign? Because we expect the larger mass to go down. See, even if we don't know the direction, the physics is going to give us the direction, so we don't need to worry. But right now at least there is some intuition that the larger mass is going to fall down and the smaller mass is going to go up, right? So then if we add up, then we see that the acceleration dv dt, or the A, comes out to be m minus small m divided by m plus capital M times g. Okay, so that is my acceleration, and if we subtract these two quantities, we find that the tension comes out to be 2 capital M by capital M plus m g, right? So these are my two, we wanted to find these two quantities, and here are the two quantities. Okay. So let us now look at a subtopic of this pulley mass system. Suppose in this pulley mass system we have a monkey. The monkey is on the pulley and it is trying to move up. And now we have to describe the net motion of the monkey and the pulley, right? So what we have is, suppose we have, so let me call this example as example number 3. So now this new example is example 3a, right? So suppose both bodies, both masses are m. There is no small mass or large mass, both the masses are capital M, and we have a monkey which is traveling upward in the pulley mass system. So let me draw this pulley mass system, monkey, right? So this is perhaps moving up, we don't know what is the direction of the velocity, but we have an animal which is perhaps climbing the rope, right? So monkey which is traveling up on the rope. So what we have to find is what happens to the masses. So what happens to the masses? So what is being asked in this problem is, what is the motion of the mass, any of the mass, because both the masses are equal, right? So let me say, well, we haven't talked about the mass of this monkey here, so we don't know what is this mass. So that is an unknown of the problem, and perhaps we don't need that mass also. So notice that this large mass, so both the mass, we don't know how the masses are traveling, whether they are traveling up or they are traveling down. Let us, without loss of generality, assume that both the masses are traveling up. The physics is going to give us the sign. So we have that for the first mass. So let us say this speed of the pulley is small v, and the speed of the monkey is capital V with respect to the fixed frame. So let us assume that the monkey travels with speed capital V with respect to some fixed frame or inertial frame, okay, and the pulley moves up Well, we are assuming it may come out to be minus v, then it is going down. So the pulley moves up with speed small v, right? So the pulley moves up with speed small v, and what we have is that the net velocity or the net speed comes out to be v minus small v, right? So the net velocity of the monkey. So when we talk about the motion with respect to, so let us keep the pulley as our moving frame, right? The fixed frame is some frame. Let me say that this is my fixed frame here, and this is my fixed frame, and the pulley itself is the moving frame, right? So with respect to the moving frame, or the net velocity of the monkey will be this small v minus v. So now with these two quantities, we are ready to write the force balance for both the masses and the monkey, right? So we see that the force balance is, for the masses we have m times v times dv dt is t minus mg, right? And the second equation of motion is for the monkey is m times d v minus v dt is equal to, again, I don't know what is the direction of the net force. So let us keep the net force to be t minus mg, right? So t minus mg. So notice that the net velocity of the speed of the monkey is v minus v. So hence we have v minus v in the second equation, right? And now from here we can find that from here if we add the two equations, let me say equation 1 and 2, if we add 1 and 2, we see that dv dt, the acceleration of the monkey is coming out to be half dv dt, right? And from here we can also find that from here if we integrate this, we see that v is equal to half capital V, or v minus v is equal to half capital V, right? So what do we have? So what we have is that the velocity of the monkey is half the velocity of the pulley system, and the velocity, even the net velocity is also the half the pulley system. So it turns out, so what have we got here? Well, this small v is the velocity of the speed of the pulley, right? So that is the speed of the pulley, and this one is the speed of the animal, speed of the monkey, right? So what have we got is that both the animal and the pulley are moving with the same speed, which is half of capital V. So that is the conclusion that we have drawn. So essentially we see that if we neglect the various realities of the motion, for example no frictional drag, nothing, and we look at the rectilinear motion of a pulley mass system, then the answers come out to be reasonably simple, where we are able to completely describe the motion of the system with very few variables, right? Here we were able to completely describe the motion of the pulley and the animal with almost minimal information, right? Okay, so then let me, when I have just now briefly introduced the concept of drag, right, or the resistance or the air resistance, let me also go and dive deeper into this phenomena of drag or air resistance via a more elaborate example. Okay, so we have, well, what have we got here? So we are talking about motion in a resisting medium. Okay, so typically let's say we have a particle, well, the ideal example could be that of a aeroplane or a jet, and the jet is moving with some speed v, right? It is moving, well, we don't expect the jet to move like this. It is going to move in the direction in which its nose is tilted, right? So it is moving with some speed v, and now there is, because it is moving in an medium which is air, there we expect that there is some drag or some air resistance on the object. Now it turns out that even this air resistance has some properties or some advantages, because this air resistance, when we try to decompose this direction or this forces, the air resistance forces, along the direction of the velocity of the object, and in the direction which is in the direction which is, what is the, I am not an aerodynamist, so maybe my arrows are not right. Let me just draw the correct arrows here. Okay, so what have we got here is, typically the air resistance on the object is of the following type, right? So it typically hits the surface normal to the surface. So now when you have an air resistance, we can decompose the air resistance along the direction of the motion of the object and in a direction which is normal to the motion of the object, right? So we have these two directions. The first direction is the direction of the so-called, the direction of the drag, since the directions are opposite. So this arrow is going to point along this direction. So this direction is going to be the drag direction of the air, and then there is a second direction which is along this direction, which is the lift direction of the object, right? So when we have an object which is moving at an angle with respect to the medium, we expect that there is a portion or there is a projection of the frictional drag of the medium which tries to lift the object, right? So you must have seen that when there is a takeoff of a flight, it always has a nose pointed upward, and that brings in the drag whose component generates a lift which helps to lift the aircraft, right? So when you have this object which is moving parallelly to the resisting medium, we don't expect any lift, because the lift will be generated 90 degrees where we do not have a component. So no lift is there when the motion is in a direction parallel to the direction of the drag, right? So let me just write down what I just said. So a lot of lines which I have mentioned. So drag forces by fluid. Okay. So when I just said is that the net force acting on the fluid is the sum of the drag plus the lift forces. So this is my drag and this is my lift. Okay, and then what we have is, if the motion is in the direction of its axis of symmetry, the motion is in the direction of its axis of symmetry, we see that the lift portion is 0, right? So the lift portion is 0, and that is what we have, that is what I just mentioned so far. So let me just see. I think we are just out of time for this particular module. We will continue our discussion on the drag and the lift of an object in the next module. So thank you so far for listening.